On October 7, 2008, Qantas Flight 72 was in cruise flight at an altitude of 37,000 feet. It was exactly 12:42 p.m. when suddenly the plane went into a dive, causing several passengers, including flight attendants, to be thrown against the ceiling of the plane, resulting in several very serious injuries. And the event didn't stop there. 3 minutes later, the plane went into another dive, injuring more people. On February 3, 2003, during the voting process in the national elections in Belgium, which was done on specific computers, one of the candidates, named Maria van der Hoeven, came out as the winner with the highest number of votes. But she didn't win the election just by having the highest number of votes. She won with a number that was mathematically impossible for the voting system used at that time. In 2009, there were many reports of Toyota cars accelerating on their own, by themselves. Several accidents happened, forcing Toyota to accept the return of the cars to investigate their causes. The cars in question were all Toyota Camry models. For many years, there had been numerous reports of sudden errors in supercomputers at the Los Alamos laboratory. They were sudden and unexplained errors that ended up corrupting terabytes and terabytes of simulations that were being run. These were errors in nuclear weapon design projects. What could be behind these events? What phenomenon was affecting these machines and causing all these problems? Qantas Flight 72 was a flight operated by an Airbus A330. The flight left Singapore for Perth, Australia. There were 315 passengers, including crew members. It was exactly 12 o'clock. There were 315 passengers, including crew members. Seconds later, when the aircraft's 3 air data inertial reference computers began providing generated data to the aircraft's flight computers. A few moments later, at 12:42 and 27 seconds, the aircraft suddenly pitches its nose down and goes into a dive, causing the passengers to experience minus 0.8 G, which made many of them be thrown against the ceiling of the plane, causing several serious injuries and fractures among the passengers. The plane descended 200 meters in a few seconds.
The G-force was enough, even with our seatbelt, to lift us off the floor and push us forward as well.
The captain managed to regain control of the plane, but a few minutes later, at 12:45:08, the aircraft went into a dive again. This time, the passengers felt an acceleration of another 0.2 Gs, and the plane descended 120 meters. The crew managed to control the aircraft and made an emergency landing at Learmonth. In the subsequent investigation, it was found that the problem occurred in one of the Air Data Inertial Reference Units, or ADIRU. This computer provides the aircraft's flight computers with 3 critical data points: the airspeed, the angle of attack, and the altitude. The way this data is sent to the flight computers is in the form of a 32-bit binary sequence. The first 8 bits identify the type of information, and from bit 11 to bit 29, they contain the actual data. So if you want to see the current altitude of the aircraft, the first 8 bits will be labeled as altitude. And the bits corresponding to the data will contain the value of the aircraft's current altitude at that moment. But what happened that day was that the label information that should have represented the aircraft's altitude was mistakenly switched, and instead of representing the altitude, it started to represent the aircraft's angle of attack. And with an extremely high angle of attack, the aircraft's protection system immediately pushed the nose of the plane down because it thought the aircraft might be flying with the nose dangerously high. But for the altitude information to be switched and start representing the angle of attack, only one thing had to happen. Or one of the bits would have to change its current state from 1 to 0, or vice versa. And this phenomenon is known as a bit flip. What could have caused the bit flip or the change in its state? Bits normally don't change their state on their own. Or do they? The investigators looked at software errors, software bugs, corrupted software, hardware failures, electromagnetic interference, but all of these were considered unlikely contributing factors due to multiple sources of evidence. The only likely event was the occurrence of the so-called single event effect, as a result of a high-energy atmospheric particle hitting the integrated circuits inside the CPU of the air data inertial reference computers. The single event effect or single event upset is a change of state caused by a single high-energy particle, such as ions, electrons, photons, and others, hitting a sensitive part of the circuit, such as a memory, RAM, microprocessor, or transistor, causing a change, for example, of a bit from state 0 to state 1, or vice versa. These events do not cause permanent damage to the circuit. They only change the state of one or a few bits and can be reversed without any problems. That's why they are considered soft errors. The main issue with these events is they leave no evidence behind. When the Airbus A330 was built in 1992, there were no regulations or requirements for aircraft systems to be resistant to single event effects. These high-energy particles can originate from radioactive materials, such as uranium, but most of them come from space, originating from the sun or other celestial bodies that are constantly bombarding the Earth with such particles. In 1973, Intel reported some strange errors that were happening with their dynamic random access memory, or DRAM. Some bits were inexplicably changing to zeros. The problem, apparently, was in the ceramic casing that protected the chip. With the increased demand for chips at that time, a new factory was built in Green River, Colorado. The only problem was that the factory was located near a large uranium waste deposit. Thus, small traces of uranium and thorium somehow ended up in the ceramic casings that coated Intel's chips. And because it was radioactive, it was constantly decaying and emitting beams of energetic particles that ended up hitting sensitive parts of the DRAMs, causing bits to change their states from 1 to 0. As a result, several system errors occurred. On May 18, 2003, during the voting process in the elections in Belgium, one of the candidates, named Maria van der Hoeven, received more votes than was mathematically possible. The votes were cast in the following way. The person who was going to vote inserted a magnetic card into the voting machine and cast their vote by clicking on the name of the candidate they intended to vote for on the screen. The vote was saved both on the computer and on the magnetic card for redundancy, and the card was later placed in a box. At the end of the day, just before the counting began, an official noticed a problem. The candidate in question had more votes than was possible. They knew this because of the way the voting system worked. So a recount was done, this time using the magnetic cards. In the end, all the candidates had exactly the same number of votes except for the candidate Maria, who this time had a lower number, 514 votes compared to the previous number, which was 4,610 votes. An increase of 4,096 votes. But how did this happen? Software experts were called in to investigate the causes. They analyzed the code, tested the computer involved over and over again, but they couldn't find the problem, nor could they recreate the same bug that supposedly inflated the number of votes. But the problem should have something to do with the number of votes. The vote numbers were stored in a 16-bit sequence, or 16 slots. Each slot can hold a value of 0 or 1 from right to left. At the beginning of the day, all the numbers would be zeroed out. With each new vote, the numbers would be incremented by 1. So, for Maria van der Hoeven to receive 4,610 votes, only one thing would have to happen. The 13th bit would have to change from 0 to 1. Knowing about the various cases of bits suddenly changing their states, the software analysts soon concluded that some energetic particle must have hit the 13th bit, changing it from 0 to 1. But, unlike Intel chips, this error didn't happen because of the presence of uranium or radioactive materials in the circuits. This particle actually came from space. The sun and other stars, as well as other celestial bodies, are constantly emitting energetic particles that travel at speeds close to the speed of light and reach Earth's atmosphere, the so-called cosmic radiation. When these particles enter Earth's atmosphere, they collide with other particles, creating pions which collide with others, decay, and create other particles such as neutrons, protons, muons, electrons, positrons, and photons. And it was one of these particles that experts believe hit the 13th bit in the voting machine, changing its state from 0 to 1. A 2010 study estimated that a computer with 4 gigabytes of RAM has a 96% chance of experiencing a bit flip every 3 days. Other studies indicate that a single event effect can occur every 14 to 40 hours for each gigabyte of RAM, and the likelihood of occurrence increases with the age of the memory. But there are already other vehicles that are much more susceptible to bit flips caused by particles from cosmic radiation. That's why these vehicles are specially built to be resistant to cosmic radiation. And that's why system redundancy is very important and is always used in these vehicles. But because computers only work with zeros and ones if a bit flip occurs, the error is extremely huge. To better demonstrate this, let's ask the computer to calculate 10 plus 10. In binary, it would look like this. And the result obviously would be 20. But if a bit flip occurs during the calculation and one of the zeros changes to 1, the result of the calculation will now be 24 simply because a 0 changed to a 1. So, can a bit flip make a rocket suddenly turn left in mid-flight and disintegrate? Yes, it can. Can a bit flip make a plane suddenly go into a dive instead of maintaining level flight? Yes, it can. Can a bit flip cause the engines to shut down early and make the rover crash? Yes, it can. Can a bit flip create a bug in GTA 5? Yes, it can. Can a bit flip cause the B-2 Spirit, the most expensive plane in the world, and the only plane that doesn't have a vertical stabilizer on its tail, to lose control in mid-flight? Yes, it can. In the case of Toyota cars, where even NASA was called in to help with the investigations, it was found that the problem was actually not bit flips, but rather the problematic design of the pedals and incorrectly sized floor mats, which ended up trapping the accelerator pedal when it was pressed all the way down.